Unit 3A, Lesson 3. In this lesson, we're going to review how to solve systems of equations, and then at the end, we're going to learn how to do linear programming problems. When solving systems of equations, there's three different methods we can use. We can use the substitution method, elimination, or graphing. So some things I want you to think about as we go through this lesson. When is it beneficial to use the substitution method, and when is it beneficial to use the elimination method? First example, we're going to solve this system by graphing. We have the equation y equals 1/2 x minus 4, and then we have the equation 3x plus 2y equals 8. So I'm going to graph both of these equations on the same coordinate plane and look for where they intersect. So in the first one, we have y equals 1/2 x minus 4, y-intercept of -4, and then a slope of 1/2 up 1 over 2, and we continue that pattern to make some points, and then construct a line through it. Now we want to graph the second equation, 3x plus 2y equals 8. If we try to use the cover-up method in this case, our x-intercept is going to be a fraction, making it a little more difficult to try to plot. So I'm going to rewrite this in slope-intercept form. The first thing I would do is subtract 3x to both sides. So we get 2y equal to -3x plus 8, and then we would divide by 2, leaving us with y equals -3/2 times x plus 4. So now same thing, we're going to go graph this by plotting the y-intercept first, which is 4. Using our slope rise over run, we go down 3 over 2 and continue that pattern. Now we can construct a graph through there. Now we have both of our equations. We're looking on the coordinate plane where these two intersect. So we're looking for this ordered pair at 1, 2, 3, 4, down 2. So at 4, -2, that would be the solution to this system of equations. It's where these two equations have the same coordinate. We could check by plugging 4 in for x and seeing if we get a value of -2 for y. When we do that, if we plug it back in, it is a solution to both equations. Now we're going to solve the same system of equations, y equals 1/2 x minus 4 and 3x plus 2y equals 8, but now we're just going to use the substitution method. We use the substitution method if we have a variable that has a leading coefficient of 1, which in this case we have a y variable with a leading coefficient of 1, and that variable is isolated by itself. So what we're going to do is take this expression 1/2 x minus 4 that is equal to y and substitute it into the other equation. So we have 3x plus 2. Now we're going to substitute in this equal value for y. So 1/2 x minus 4, and that is equal to 8. The reason we use the substitution method, if we look at this equation, we have two unknown values for x and y. After we substitute, now we just have one unknown value, x. So we go through and simplify using basic algebra. 3x plus 2 times 1/2 x is just going to be 1x. 2 times -4 is -8, equal to 8. So now 3x plus x would give me 4x. If I add 8 to the other side, I get 16. Now divide by 4, we get x equals 4. Now we take this value of x, substitute that in for x in the original equation. We get y equals 1/2 times 4 minus 4. So y is equal to 1/2 times 4 is 2 minus 4, which is -2. So our solution to this system is 4, -2, which is what we got in the last problem when we graphed it. Using the same system of equations, now we're going to go through using the elimination method, also called linear combinations. We use this method if we have a variable x or y where the coefficients are the same, except one's positive and one's negative. For instance, if we had a -4y in one equation, if the other equation had 4y, a positive 4y, then we could combine those using elimination and solve simply. In this particular problem, we don't have any variables lined up with the same coefficient, one positive, one negative, but we can rearrange the equations to make that true. So I'm going to choose to rewrite this first equation. I want to get x and y on the same side, so I could subtract 1/2 x and bring it to the other side of the equation, which would give me negative 1/2 x plus y equal to negative 4. So now I rewrite that equation down below, negative 1/2 x plus y equal negative 4. I'm looking at my x variable and my y variable. I want to eliminate one of those. So I have to make the coefficient, if one coefficient is positive in the first equation, it has to be negative in the second equation. I'm going to choose to eliminate the y variable in this case, just so I don't have to deal with that fraction. So if this is a positive 2y, in the second equation, if I want to eliminate that variable, I have to make it a negative 2y. So I'm going to multiply the whole equation by negative 2. So I go through and distribute. Negative 1/2 x times negative 2 is going to give me a positive x minus 2y equal to 8. So now I'm ignoring this part of the equation, and I'm going to combine my first equation with my new second equation that I just rewrote. So I'm taking 3x plus x to get 4x. Positive 2y and negative 2y make 0. So I have 4x equal to 8 plus 8 is 16. Now if I solve for x, divide by 4, I get x equals 4. To find the value of y, it doesn't matter which equation you choose, the first one or the second one. I'm going to choose the first one because y is already isolated by itself. So y equals 1/2 times 4 minus 4. 1/2 times 4, 2, minus 4 is going to be negative 2. So the solution to this system of equations is 4, negative 2. So that's how you use the graphing method, linear combinations, also called elimination, and substitution. The last thing we're going to discuss in this lesson is linear programming, which is the process of maximizing or minimizing a linear function called the objective function. This function gives a quantity that is to be maximized or minimized, and it is subject to constraints. The constraints are going to be linear inequalities that give us a region. That region is called the feasible region. It can be bounded or unbounded. We're going to use that region, find vertices, plug those ordered pairs contained by the vertices back into our original objective function to see what values are potentially maximum or minimum values. So this slide shows the difference between a bounded region and an unbounded region. The green linear inequalities represent our constraints. If they contain a region called the feasible region, this would be an example of a bounded. Okay, we have this region that's contained, it's some polygon. The difference between a bounded and unbounded, in the unbounded over here we have our constraints, and we have our feasible region. We have no limiting constraint that contains the maximum values, so this feasible region would go up. That's why it's called unbounded. So the last example, find the maximum and minimum value of the objective function with the given constraints. So we have c equals 3x plus 4y. That's our objective function, the function we're trying to maximize and minimize. And then we have the linear inequalities. X is greater than or equal to 0. Y is greater than or equal to 0. And x plus y is less than or equal to 8. Those are the constraints. They create the feasible region. So what we're going to do is first graph all of our constraints on the same coordinate plane. Once we have all these linear inequalities graphed on the same coordinate plane, we're looking for the feasible region, where the shaded region would be, where all of these overlap, which is going to be contained, in this case, in this right triangle. Okay, so we find our feasible region. Now we have to identify all the vertices and write those ordered pairs. So we have 0, 0. This one would be 8, 0. And we have 0, 8. The last thing we're going to do is plug each of these ordered pairs back into our objective function and see which values give us a maximum and which values give us a minimum. So now I plugged each of those ordered pairs back into the objective function and simplified. When I plug in 0, 0, I get 0. When I plug in 0, 8, I get 32. And when I plug in 8, 0, I get 24. So we're looking at these corresponding y values. The minimum is 0, which occurs at the ordered pair 0, 0. The maximum is 32, which occurs at the ordered pair 0, 8. So that's the process of linear programming. We're trying to maximize or minimize our objective function. We do that by graphing the constraints and determining the feasible region. Once we have the feasible region, we're taking the vertices contained by the feasible region, plugging those back into the objective function to see where the maximum and minimum values occur.